Hello and welcome. Today I'm going to talk about a new topic called impulse and momentum. Impulse and momentum. Now, by now, you should be familiar with the concept of energy. All right, so this is based on the assumption that you already know what energy is: conservation of energy, kinetic energy, potential energy. All right. Can you learn momentum and impulse without these? I guess you can, in a way, but it's good to know about energy, because when we do calculations about collisions, energy, the concept of energy, kinetic energy in particular, will play a role in the classification of collisions. At least you need to know what energy is then, right? And also you'll need to know basic things about dynamics, like Newton's 3 laws, especially Newton's 2nd law, to understand what impulse means. All right, so let's start with what we know about kinetic energy. Now, kinetic energy, I'm going to use the symbol K, is defined as 1/2 mv squared. M is the particle's mass, and v is its speed. Okay, speed is the instantaneous speed, which is a scalar quantity. Okay, v just stands for the magnitude of the velocity, which is a vector. Okay, but you're taking the square of it, so you lose the information regarding the direction. Okay, there is no direction with kinetic energy. Kinetic energy is simply a scalar. Kinetic energy is a scalar quantity independent of direction. So if you throw a ball upward or downward or with an angle, as long as you throw it with the same speed, it'll have the same initial kinetic energy. All right? So besides the speed, it contains mass. So energy will give you an idea of the impact you will have if that thing you throw hits a glass wall or something. Okay, will you break it or not? Will it break it or not, for instance? It gives you an idea. Okay, though it's not enough to analyze collisions in general. Okay, 2 cars colliding, or on a pool table, billiard balls going under collisions. If you want to analyze what happens during those collisions, you'll need a quantity which also carries the information about the direction of motion. Okay, when 2 balls collide like this, maybe they will go back that way. But what if there's some angle involved? All right, what we call a glancing collision. Or what if they're moving in the same direction? Let's say you're on a highway, you're driving faster than the car in front of you, and you hit the car. All right, so in problems like this, the direction definitely plays a role, at least in determining what happens after the collision, right? So we'll need a quantity which still contains mass and velocity, not just speed as kinetic energy does, but also direction. So that's what momentum is, pretty much. Okay. So I'm going to use the letter P for momentum, little p. Now you may remember the letter P from energy. Power also is P, but power was a scalar quantity as well. This P, small p, stands for momentum, and it is a vector. I just take mass and velocity and multiply them. Okay, That's the definition of momentum, simple as that. What about the dimensions of this quantity? Like we have mass here, which is measured in kilograms. Okay, the dimension is mass, just m. Velocity, on the other hand, measured in the standard system, meters per seconds. So we're talking about length, capital L. These square brackets stand for dimension of a physical quantity. And seconds in the denominator, which corresponds to time, right? So L over T multiplied by M, that is the dimension of momentum, ml over T, and the unit is kilogram meters per seconds, right? The unit is kilogram meters per seconds. That's the unit for momentum. Now you could compare the momenta of objects, let's say a tennis ball versus a, I don't know, a bowling ball, right? So a tennis ball versus a bowling ball, which is much heavier, right? MB versus MT, all right? I mean, you can look up the numbers in kilograms, find out how much they weigh and all that, but can they have the same energy and can they have the same momentum, okay? They may, if you want these two to have the same energy, same kinetic energy, then with what speed you should throw them, you know, that could be a practical problem. V versus V prime, all right? So if you want to have them to have the same energy, then 1/2 mt v squared. Simply equate this to the energy of the bowling ball, which has a much larger mass. So you don't have to throw it that fast, right? So v prime squared. Okay, same energy. This is a G here. All right, so this will give you an idea how much damage you'll cause, you know, if you throw this to a, I don't know, some object or person. But a similar analysis could be done for momentum. Like, what if they have the same momentum? How about same momentum? Then you will compare the two momenta using the definition of momentum over there, like this, all right? So if you, let's say if MB is 20 times greater than, if MB is 20 times greater than MT, I don't know the exact numbers now, I'm just making this up. Suppose the bowling ball is 20 times heavier than the tennis ball. This means for it to have the same momentum as the tennis ball, it's enough if you just throw it with a speed equal to 1/20 of the speed of the tennis ball, right? That's what it means. So the relationship there is inverse. There's an inverse proportionality, but it's still linear in a way, if you get my drift here. So it's equal to 1/20, just an example. That's not the case for the energy, right? I mean, if MB is 20 times greater than MT, well, you have to take the square root and see how what will happen to the velocity. So it's not possible to have for two objects to have the same momenta and the same energy at the same time, right? As long as you have different masses, masses as constants, you can easily see that they either have the same momentum or same energy. So that's one of the differences. That's what I'm trying to say. The number one difference, momentum is a vector quantity, which has a direction and a magnitude. Kinetic energy, on the other hand, does not care about direction, which may be helpful in some calculations, but not so in other types of calculations. All right? That's the definition of momentum. Now, momentum itself is good, the momentum at an instant, because velocity may change, right? So P here becomes some other P, as the object moves. So we may think about the change in the momentum, all right? That's a good concept to consider after just the basic definition. So how about the change in momentum? As usual, we're going to use the letter Greek delta for change, delta P, okay? P later minus P before, or P final minus P initial, okay? There are various notations here. For now, I'm just going to write P final, let's use F, P final minus P initial, okay? Two separate instances, all right? When you calculate this, you got to keep in mind that momentum is a vector quantity, all right? Even if the motion involves just one dimension to work with, all right? The car is moving this direction, later it's moving in the opposite direction, and you're comparing the two instances. You got to keep in mind it is a vector quantity. So you pick a direction and call it positive, the other one will be automatically negative. Or if it is in two dimensions, you got to subtract the vectors. So if the first one was a car moving in one direction, okay, this is V initial, okay, this is when time is 12:32 p.m., okay, and then you check back again at 12:40 p.m. and you see the car either going backwards or going forward, but in the opposite direction, with a velocity equal to Vf. All right, so when you consider the change, you got to be really careful now. Okay, so let's take the initial direction as positive. This is the positive direction, positive x, let's say, okay? And V initial was, let's say, 15 meters per second. Now, Vf, if I just write it like this, like speed, okay, which is just the magnitude of this, let's say is 20 meters per second, okay? But now it's moving in the negative x direction, in the opposite direction. If you say, okay, to find the momentum difference and assume this is a toy car and the mass is just 1 kilogram, mass is 1 kilogram, and you may say, oh, I have 20 kilogram meters per second, that's the final momentum, and the initial momentum was 15 kilogram meters per second, the difference will be 5, okay? That's going wrong. That's going to be wrong if you just subtract 15 from 20. You can't do it like that because you're not subtracting vectors if you do that, okay? Here's how you do it the correct way. If the car is moving in the opposite direction, it's a negative velocity, okay? The component is negative. Therefore, the momentum is also negative. So negative 1 kilogram times 20 meters per second, or 1 kilogram times negative 20 meters per second, minus, this minus comes from the definition of delta, minus the original momentum or initial momentum, 1 kilogram times 15 meters per second. All right, therefore the difference is negative 20 minus 15, negative 35 kilogram meters per second. All right, that's how you take the direction into account. And that's one-dimensional. In 2 dimensions, same idea. Let me use vectors in 2 dimensions, maybe billiard balls, right? So let this be a pool table. Here's a pool table. Okay, and now you have a ball here. Okay, and another ball over there. Okay, now you kick this with, not kick, you hit this with the, I guess I don't need that, with the stick. All right, giving it an initial velocity. So the initial velocity, let's use a different color, red, will be pointing in that direction. This is the direction of the velocity of the cue ball that you're hitting with the stick, right? So let's call this V1. Okay, let's call this M1 and M2. Maybe billiard balls have the same masses, but in general, they can be different, right? So this will be called V1, the initial velocity of the ball. Now, when this ball hits this guy, all right, what will happen? Well, M2 will be moving. Let's say this is the first picture. Let me just draw what happens after the collision now. This will be a glancing collision, right? So M2 will now move this way. And M1, which was originally moving this way along the initial direction, will now be moving like this. This happens all the time when you play pool, right? Let's call this V1, but to denote that it is after the collision, let's put a prime here, V1 prime. Similarly, this will be V2 prime. Okay, initially V2 was 0 because it was stationary, it was at rest. So V2 was 0 in the beginning. This is before the collision. This is after the collision. Okay. Now a note about notation here. Every book has its own notation. Okay. Here I just used the letters V for velocity and M for mass. Those are almost the same. Some books use a U for velocity, but not very common. But what changes is how you number them or how you label them. All right. So I used here 1 and 2 for the objects, 2 objects, 2 balls. And I used unprimed velocity for before, primed velocity for after. But in some books, you will see 1 for before and 2 is for after. Or you will use the letters I and F, okay? So those are also options. Let me just make a list here. Before, Okay, I'm gonna need to move that board here. Let me just maximize it again. All right, and after I did it again because I hit this button here. All right, try to avoid that. So either use V1 and V2, where 1 and 2 means object 1 and 2, and the after velocities are just 2 primed ones. That's one way of doing it. Or use the letters I and F. So V1 I, V2 I, and then V1 F and V2 F. And some books, not very common, but they do it. They use the numbers 1 and 2 for before and after. Okay, so you will have, let's say, then how are you going to name the objects? They name it as A and B. So A, the first ball, let's say, VA1, and the second ball, B, VB1. 1 means before, and 2 means after. So VA2 and VB2. Okay. So these are the notations I've seen. Maybe there are other notations. Doesn't matter how you notate them, as long as you're consistent. All right. So this is an example where you have to add vectors. Again, this is why I brought it up. So consider what happens to V1, for instance. All right, let me switch back to the arrow. So this was V1, and now I have another vector, and this will be V1 prime. So something like this. Okay, don't worry about the length of this, just a representation right now, just to make a point here. So what I need now is the difference. Okay, so let me label them now so you know what I'm talking about. This one here is V1 in the picture, V1. And this guy here, V1 prime, the after velocity of the first billiard ball, the cue ball, and this becomes delta V now. Delta V, which is V1 prime minus V1. Okay, now it's not delta P, but it's easy to get delta P. You just multiply everything by M or M1, and you get M1 times delta V equals M1 times V1 prime minus M1 times V1. Okay, so what you have here is delta P, or P1, because it's the first ball, is equal to P1 after minus P2 after, which is this, right? Same thing, but this is how you work it out in 2 dimensions. Same thing in 3D, okay? So, just be careful with the direction, okay? Let's say you're throwing the tennis ball to the wall, all right? So let's think about that. So here's the ball. You're just bored and you want to play with the ball. You just sit here and throw the ball, all right? So Here's the ball. You're going to throw it this way. All right, it's going to bounce off of the wall. Of course, once you throw it, it becomes a projectile. So it's going to follow a path like this. Under the influence of gravity, it's going to become like this. So by the time it reaches the wall, the velocity as a vector will look like this, okay, with a smaller angle. And think of this bouncing like light reflecting off of a mirror. You know, it's not exactly the same, will never be the same, but you expect the ball, you know, to become a projectile after the collision with the wall with an angle close to this, but only in the other direction. Okay, something like this. It's not too unrealistic. All right. So it's going to become a projectile again, and you're going to catch it, right? So you're going to, all right. As the ball flies like this, you're going to catch it, and then the whole thing will repeat itself, all right? So what we care now is not the vector, velocity vector you throw it with, but right before and after it hits the wall, all right? That's what we're after. So I'm gonna name this P later, PF, and this is P before, right before the collision with the wall, all right? So then delta P will be found using the regular laws of addition of and subtraction of vectors, like this. Okay, this will be delta P. All right. So let's solve a problem. Let's say a basketball player. Here's a basketball player. An example. Okay. All right. So here's the basketball. Throws it this way. And I'm going to draw the floor here. All right. So you expect this to move along this direction, initial direction, and then it'll bounce. All right, like this. All right, so this is where it bounces. Okay, and I'm kind of ignoring the projectile nature of the ball because it's going to be a parabolic path, not a straight line. I'm just drawing the velocities right before and after the collision. All right, let's use numbers. How about that? Let me just say, okay, let's see. Let's see, this is, let's say, 40 degrees. 40 degrees. And let this be 35 degrees, okay? And the mass of the ball is 1 kilogram. It's usually less than that, but let's say it's 1 kilogram, all right? And the speed before, let's say, is 4 meters per second. 4 meters per second, and after 3 meters per second. Okay, video. All right, so let's solve this problem, meaning let's find the change in the momentum. But keep in mind that momentum is a vector quantity. And let me stop the video now. I'm going to continue this in the second video.